on. Okay, so we are going to discuss about neural networks now. Can you all see my screen?
Yes, sir.
Great.
Yes, sir.
Okay, pen is working. Yeah. So, what are neural networks? So the details you will see in the videos, but just this is an overview. So you remember we have a so this is a classifier. You have some input X, and your output is one of the classes. So I will call it as a multi-class classifier. Multi-class classifier. The output is, oh, sorry, I have to draw in white. The output is Y. So it is like you have here, multiple possible classes, and your output is a vector Y, which is equal to probability that your output class is some class, let's say Y given X, right? So my Y could be anything between the total C classes. So, okay, if it starts from 0, then C minus 1. Right? There are total C classes. So when it is like, so to give a concrete example, these are different possible classes. These are different phonemes like e, o, like that. A. All these are different phonemes or different vowels. And my probability, you have to tell probability, what is the probability that the vowel which I have spoken is a, or it is e, or it is u, like that. Is this clear? Is this clear?
Yes, sir.
Yes, sir.
Okay, great. Now, you do the same thing with Gaussian mixture models. In Gaussian mixture model, same thing is happening. This black box is just a Gaussian mixture model, or it has a Gaussian distributions for each vowel separately, right? So in GMMs, what do you get? Okay, let me call this as function f. So if f is a GMM, Gaussian mixture model, then what does it give you? What does a GMM? What is the output of a GMM? What is the output of a GMM? What is the output of a GMM? Jayant or anybody? What is the output of a GMM?
Sir, the probability.
Probability, what probability? So you have X and you have Y. What is
Probability that class y equal to some small c given x bar.
Is this the output of a GMM? Anybody? So good attempt, Jayant, but maybe the answer is not correct. You have to think harder. Anybody? Who all are there? Who are the participants? 9 participants total. Akanksha, Vidhesh, Jaya, Jayant, Roshan, Sumit, Suraj, Abhishek. Yeah, please tell what is the output of a GMM, a Gaussian mixture model?
GMM output is the multiplication of transition probability, emission probability, and
That is HMM, not GMM. Gaussian mixture model. What is the output of a Gaussian mixture model? So Gaussian mixture model, like you have your X here, let's say X1, X2, something like that. And then you have some data here. And Gaussian mixture model will just try to model this with one Gaussian and this is another Gaussian, and it will say this is the probability distribution of X, right? Right? It will tell you probability of X is equal to summation of, let's
categorical
say,
distribution and
Wi, where I is equal to 1 and 2. There are two Gaussian. Then normal of X given mu I, comma, sigma I. This is a Gaussian mixture model where your W is kind of categorical distribution, or the sum of all W is 1. And W is greater than equal to 0. Right? That is a Gaussian mixture model.
yes sir, yes sir.
How do you use a Gaussian mixture model for classification? Who would like to answer?
We were modeling each class by a Gaussian with a particular mean and covariance.
Okay, so to make your things simpler, I will modify the notation a bit. I will say probability of X given theta. Theta is a vector. So theta includes all the parameters of the Gaussian, means it's mu, sigma, etc., etc., etc. So my theta, it includes all the mu's, like mu I for all I, sigma I for all I, and also wi. Sorry, I should have added that as well. Like these are the parameters of your GMM, right? For all I. This is basically it is a set of all parameters. We call it as theta. So given my theta, my P of X is this, right? Okay, now tell me what you are saying, Avdesh. Yeah, please continue. Please carry on.
For each class, we are going to model by using a particular mean and covariance. And to estimate this mean and covariance, we use maximum likelihood approach.
Yeah, given theta C for each class C. You can say it like this, or you can draw a line. Line means conditioning, and this just it says that these are parameters. These are given parameters. You can draw a line or a semicolon. Both are acceptable. So this is basically uh, this is one GMM. This is GMM, and then you have multiple GMMs. C can be uh, 1, 2, so on up to number of classes. If you start from 0, then number of classes minus 1. Right? This small c. Right? This is my Gaussian mixture. These are my Gaussian mixture models for different classes. So for example, my sound A will have one theta, let's say theta 0. My sound EE. E will have another kind of theta, which is theta 1. Okay, let us say 1. Like that. E, E, U, U, A, A, O, O. So this will have theta 2, this will have theta 3, this will have theta 4. Okay, now tell me, we have obtained this. Now, how do you use it for multi-class classification? Given a new, now you will train them from samples, right? You will train the theta O from all the sounds of basically all the windows which correspond to sound. You will train your GMM, this GMM, and then this all the windows which correspond to E sound, you will use them to train your this GMM, right? Use all windows of A to train theta 0, right? Comma, so on, and for all classes. Okay. Now tell me, how do you use now? How to classify a new sound? How to? Or basically it means a feature vector, right? X. Now this is test time. This was train time. During training, you use all the windows. Now during testing, how do you do testing? Inference. How do you do it? Avadhesh? Please tell. Please tell, Avadhesh. Don't be afraid. Means, I think even if you are wrong, no problem.
Okay, find the probability that this new feature vector belongs to a particular class. Uh, can we use KNN?
Yeah, whatever you like. No, don't use KNN or anything. You already have trained a model. You just tell me how are you going to use this model to classify the new sound.
Can we use here hot vector, one hot vector?
Whatever you want to use, just tell me how do you classify given this model.
We will assign one hot vector for these classes, and wherever value is 1, then we can say that this class is present here. This phonemes is present here. Am I
Okay,
right?
tell me. So what are you saying? If you have X, then
We can make one hot vector for 5 classes here, because we know
what will be the entries of the one hot vector?
uh,
Yeah,
first it will
okay.
then which class is present there.
Yeah.
I think one hot vector is that class will present then their corresponding value will be 1, and mm, if class is absent, then their corresponding value is 0.
Okay, so yeah, we have to make a one hot vector, but how shall we make a one hot vector? I have only X known to me and the thetas are known to me, theta C are known to me. How
Sure.
yeah.
Sir, the thetas represent Gaussians corresponding to each class. So from that we can estimate the probability of getting X with respect to each Gaussian mean.
Okay, probability of X given, or means the parameters
Theta,
are given.
theta naught, theta 1, so on, theta C minus.
Theta naught. Here probability of X. Yes, very good attempt. Very good try. Very clever answer. Then, okay, in this way I will create my vector. So then what next? What next?
We can use some activation function to normalize.
No, there is no activation here in Gaussian mixture model. Gaussian mixture model has no activation function. It is just a Gaussian mixture model.
After that, the classification part.
Then how shall we classify?
We can either take maximum, or if we want to soft classify, then we can use something like sigma activation.
Activation function, how shall you use? Activation function, I don't think it's needed. Why do you need activation function here?
Okay, so then we can directly say whichever has the highest probability
Basically,
X bar belongs to
C star, my winner class is basically
argmax.
argmax over small c. And instead of this, I can simply write something. So simply p of is that what you're suggesting?
Yes, sir.
Okay, good attempt. Good try. I think this is a very good try. But what we do in practice is very similar. We do argmax over c.
EM algorithm we use.
No, EM is used for training. You have already trained. Now this is inference time or testing time. Here you don't need an EM algorithm. What you will say, P of theta, or you can say, sorry. This is what we are maximizing. This is called maximum a posteriori estimate. So now we do not know this term, right? We only know these terms. We have to somehow convert this into this. How shall we do that? Actually, okay, I can
Yes.
do one modification. Instead of saying theta c, I will just say theta, which is basically my theta is, it contains all theta I. Theta 1, start from 0, right? 0, theta 1, so on. My theta is just everything together. Right, because C is already, it is labeled here, then theta can be just put in one basket. Okay, now tell me, we don't know this value, we only know this value, which is basically, okay, actually, let me, I can say one possibility. So this is basically equal to argmax over small c, probability of x given y equal to small c, comma, theta, right? Let me erase this. Right, we can write it like this, right? We just need to know all the thetas, and we need to know what is the y. Then I correspondingly pick that theta from here, that theta c from here, and then estimate p of x given theta c. Right? Now tell me, how do I convert this into this? Means I don't know this term. I only know these terms.
Base.
By
Base
using
two.
Bayes rule.
Very good, very good. We will use Bayes rule. So this remains same, no change here. Argmax c. This term becomes p of Tell me x. Yeah.
P of x given y equals to c,
X given y equal to c. Then
comma theta
yes.
into py equals to c.
Let me make some space. I'm running out of space here. Uh-oh. Okay. Now tell me. Then this is
Py equals to c.
hmm.
Probability of
Then
divided by p px
hmm.
x given theta. Yes, sir.
Right. Now this term is not a function of c, so this term can be ignored. Right. This term is not a function of c. Therefore, ignore, because we only want to maximize this term with respect to c. This term is not a function of c, so this can be ignored, right? So what we get finally is argmax over c, probability of x given y equal to c comma theta times probability of y equal to c given theta. Right? So this term is, it comes from your GMM. From GMM. What about this term?
Prior knowledge.
Prior knowledge. Very good. So this term basically can be calculated. For example, in English language, some vowels are very common and some phonemes are very common. Right? Some phonemes are very common. For example, which phonemes are common and some phonemes are rare or uncommon. Which phonemes are uncommon? Tell me which phonemes are very common and which phonemes are uncommon. Or tell me alphabets. I think phonemes is difficult because we are not linguists. We may not be able to tell this answer. At least alphabets we can tell. In writing, although we are not dealing with alphabets here, but still, uh, just to know if you are able to think. Some alphabets are common, some
Uncommon is Q. Q will not come frequently.
Q is uncommon. Yes, Q.
Z
Z,
x
Yes.
X,
These are uncommon ones. And the common ones are,
Vowels
a
are common.
D,
huh?
a
Vowels are common.
Vowels are common. Yes. Good. Yeah. So, so there are so similarly there are some phonemes which are common and some phonemes which are uncommon. Now, can you think of some phonemes which are uncommon and some phonemes which are common?
A are all common.
A, E, these are common. Then, which are
I,
uncommon?
A,
Huh?
A, E,
I don't know. Maybe we can say F is uncommon. It's not very common.
Fricative, all fricatives,
fricative,
plosives.
Fricative. So you know the terminology of phoneticians. Nice. per. Um,
So
per is still, I think, common. Sure.
common.
Sure. Okay, like that. So we can have many. So basically, we can say that we can condition our model that the common ones are picked more frequently. So we basically get them from our transcription. So if we have a huge text, um, so if you estimate from phonetic transcriptions. Phonetic or phonemic transcriptions. From there, you can estimate these numbers, right? If I give you Wikipedia text of which has all the alphabets, and I ask you what is the probability of A, you can just compute the number of A's which are occurring in total, right? So probability of A, this capital A, given the Wikipedia text. Just sorry, no need to write. And you can find it out, right? Probability of A is number of occurrences of A divided by total number of alphabets. Similarly, so this is from Wikipedia. For example, from Wikipedia. Similarly, from phonetic transcriptions of some text. Generally, people use, let's say, if you have training data, um, it has got your audio and the corresponding phonetic transcription, right? That same phonetic transcription you use, phonetic transcription in training set. The same phonetic transcription you use to train your P of a particular sound. Same thing, just number of occurrences of this sound divided by total number of occurrences of all the phonemes present, right? So that's how you compute this. And then you normalize. And then, okay, once you obtain this, you can also normalize it so that this whole term becomes a PDF. That normalization is also possible. But anyways, if you want to just compute the maximum, then we need not do the normalization. Okay, is that clear? So now so this part is clear. This was, I think we have just covered when F is a GMM. Now, if F is a Gaussian, F is a neural network. So what you do, neural network is basically, it is a model. It has got some input X, and the output is probability of Y equal to a particular class given X, comma, theta. And these thetas are the parameters of the neural network. This is a neural network, right? And theta are the parameters of this neural network, which are the weights and the biases. Mostly these two are the parameters of the neural network, weights and the biases. Okay, so that is it. And it gives you the probability of Y given X comma theta. So you can directly use it in your model. Now, Now what we are doing is, I want to open up this black box and tell you what exactly is a neural network. Neural network is consisting of neurons. Let us see first what is a neuron. Neuron has got inputs. Input is a vector. Let's say my vector. Let us call it as what? Let me call it as some x. And the output is, so neuron has two steps. I will just break this neuron into two parts. It has two steps. One is weighted sum, and the next is a nonlinearity. So what is this weighted sum? So let us say my output is h here, h vector. So my h, let me call it as h. Let us call this as xi. The elements are xi. The elements here are hj, and the elements here are vj. So my hj is equal to w j
into xi.
and summation over all I. This is my hj, right? Simply a weighted sum. To find hi, I will multiply this matrix. In matrix notation, it will be simply h is equal to w times x. Right? But in the element-wise notation, it is just this. Is this clear? Is this clear? Somebody would like to speak? Is this clear?
Yes.
Okay, then we have Vj. Vj is simply a nonlinearity, f of hj, element-wise nonlinearity, right? And this f could be any function. Uh, it is a monotonic function. My f is a monotonic function. Uh, it could be of any shape, like this, and it is bounded mostly. Need not be bounded all the time, but yeah, generally it is. But no, there are examples where which are not bounded also. 1, 0, or it could be like this. This function is 1 upon. So let us. This is my h. Sorry, this is my h. This is my v, and my v is equal to 1 upon 1 plus e to the power. Is it plus h or minus h? When h is plus infinity, it is minus h.
Minus h.
Yeah, thank you. 1 plus e to the power minus h. It's a nonlinear function, but the property is that, see, when your h is very large, like towards here, then this term will be almost 0, and this becomes 1 upon 1, which means the value is 1. And when your h is very small, close to minus infinity, like towards minus infinity, then this term becomes very large. E to the power minus minus infinity means very large term. So v becomes almost 0, 1 upon very large term. That's how, so this is one kind of nonlinearity. Then this is called tan inverse h. So my y lies between what range? What range? When my v is tan inverse h, then my v lies between what range? What is the range of tan inverse?
Pi by 2 to minus pi by 2, minus pi by 2 to pi by 2.
Yes, minus pi by 2. When my h is minus infinity, tan becomes minus infinity when theta is minus pi by 2. And this is pi by 2. Thank you. like that. I can have different kinds of non-linearities, and that's what. So this is one neuron. Is this clear? If you have understood a neuron, then a neural network is the same thing. Basically, it's a combination of many neurons. Now I will draw a neuron as a circle. So these are my xi. Let's say this is my x1, or let's just call it, let the numbering start from 0, x2, right? And in general, this vector will be called x or xi. The element can be called as xi. And then we have this. It will be outputting a v, v0, v1, v2, v3. I can have any number of neurons, no problem. v4, right? And to calculate my v0, I will be taking all of them, sum them up in a weighted way, right? And then apply the non-linearity. So this neuron will be outputting 1 v0. Similarly, the here also take everything, sum them up in a weighted way, and then apply the non-linearity. You will get v1, and in this way, like for everything, like here also you get all three inputs, and then you sum it up. Like this is my one layer of neural network, and I will call this as, let's say, vj. All of them I denote by the index j. Or now I can have multiple layers. Who stops me from making another layer which takes this as input, right? I can have another layer with any number of neurons. Nobody is telling me to use that many number of neurons only. I can choose any number of neurons. Of course, I have to find out which number will give the best performance, and that I can empirically determine. I will try different numbers, and whichever gives the best results, I will say, yeah, that is the number to go with, right? And then the output of this will be called something else. Now I can call it as VK, but since there could be hundreds of layers, practically, okay, yeah, there are some really massive neural networks which can have 100 layers also, which are very difficult to train, I must say. But yeah, okay, let us say 10 layers is a common thing. We have 10 layers. So we can simplify our notation. Let us call this as I0 for the layer number 0. Let us call this as I1 for layer number 1, as I2 for layer number 2, right? And I can have L number of layers, and then I will call VIEL, right? So let us say this is my, now let us say this is my output layer. Okay. Here I will have VIL minus 1, right? Where L is the total number of layers. And let us say this is my output layer. This is my equal to Y. This is my output layer. So basically, this output corresponds to A sound, E sound, O sound, like that. This is my output layer. Now, the thing is, my output layer, I want the interpretation to be like, it should be a probability distribution, probability of my Y, IL minus 1, given X, and theta, right? I want this interpretation to be a probability distribution. Basically, I have to somehow convert these numbers, the V's, or you can say the H numbers. So I have some H, right, which are just weighted sums, right? So how do I convert them into a probability distribution? So I have to apply a suitable transformation. to f of all the h. So it need not be element wise, it could be acting on the entire vector also. So that's what we are now concerned with, how to choose this f. So a possible choice is like this. You can say e to the power h I l minus 1 divided by sum overall, because you know the sum should be 1. So first of all, each term should be positive. So this term is definitely positive. This term is definitely positive. No matter, even if my h is negative, this term will be always positive. Right? So this is always greater than 0. Right? Always positive. And then I have to normalize that sum. The sum should be 1. So I will say e to the power h I dash l minus 1 and sum over all I dash l minus 1. You basically sum over all the terms. Now, what can you ensure? You have ensured my each vi l minus 1, or I will say y okay, all right, is greater than 0 and sums up to 1. That's it. This is what you have ensured. So this is all about neural networks which you want to study, which you want to use in your speech recognition problem. Multi-class classification neural network. So this is my neural network. Anybody has any question here? Anybody has any question here? Okay, if not, then I would like you to go through the lecture videos which I'll be uploading, and then let me know next week if you have any questions. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.